Welcome everyone to Dr. Carminati's YouTube channel. I'm thrilled you're joining me today for an exciting deep dive into a topic that's shaping the future of cybersecurity. The approved Federal Information Processing Standards, or Fips, for post-quantum cryptography. Specifically, we're exploring the document available on Nist's website titled Nist Fips 205, which focuses on the stateless hash-based digital signature standard. If that sounds like a mouthful, don't worry. I'm here to break it all down for you in a way that's clear, engaging, and accessible, even if you're brand new to this subject. I'd love for you to stick around, share your thoughts in the comments, hit that like button if you find this helpful, and subscribe to the channel for more content like this. Let's get started. Imagine a world where the most powerful computers can crack the codes protecting your bank account, your emails, or even national security secrets in mere seconds. That's the challenge quantum computing poses to our current cryptographic systems. Today's encryption methods, like RSA or elliptic curve cryptography, rely on mathematical problems that regular computers struggle to solve. But quantum computers? They're a game changer. With their ability to perform complex calculations exponentially faster, they threaten to unravel the security we've depended on for decades. That's where post-quantum cryptography comes in. It's our shield against this looming quantum threat. And the document we're diving into, Nist Fips 205, represents a huge step forward in that mission. So what exactly is Nist Fips 205? This document, published by the National Institute of Standards and Technology, or NIST for short, lays out a standard for a digital signature algorithm called SLH-DSA, which stands for Stateless Hash-Based Digital Signature Algorithm. NIST released this as part of their broader effort to establish post-quantum cryptographic standards. This process kicked off years ago when they called on experts worldwide to submit quantum-resistant algorithms. After rigorous evaluation, SLH-DSA emerged as a winner, and now it's officially approved as Fips 205. This isn't just a technical paper, it's a blueprint for securing data in a quantum future. Let's meet the minds behind this document. The authors include a team of NIST experts: David Cooper, Quinn Dang, Jake Doliscani, Andrew Fregley, Morris Dworkin, Scott Rose, and Christopher Selly. These folks bring a wealth of experience in cryptography and cybersecurity. David Cooper, for instance, has spent years researching cryptographic protocols, while Quinn Dang focuses on secure algorithm design. Morris Dworkin, another key contributor, has authored multiple NIST standards, making him a veteran in this field. Together, they've crafted a document that's both technically robust and forward-thinking, ensuring it meets the needs of government agencies, businesses, and anyone relying on digital security. Now let's unpack the star of the show, SLH-DSA. At its core, SLH-DSA creates digital signatures, which act like virtual fingerprints. Think of a digital signature as a way to prove that a message or file comes from you and hasn't been tampered with. If I send you an email with a digital signature, you can verify it's really from me, not some imposter, and that nobody altered my words along the way. In a world where trust is everything, especially online, digital signatures keep us safe. SLH-DSA does this using a hash-based approach, which is a big deal because it's one of the few methods experts believe can withstand quantum attacks. Here's how it works in simple terms. SLH-DSA builds on something called a hash function. A hash function takes data, like a message or a file, and scrambles it into a fixed-length string of characters called a hash. This hash is unique to the input data, so even a tiny change, like adding a comma, produces an entirely different hash. SLH-DSA uses these hashes cleverly to create signatures. It relies on a structure called a Merkle tree, which organizes multiple hashes into a hierarchy. Picture a family tree, but instead of people, each branch holds a hash. The top of the tree, called the root, ties everything together, allowing someone to verify the signature by checking the root against the data. What's brilliant about this is that it doesn't depend on the kinds of math quantum computers excel at breaking. It's all about hashes, which quantum machines don't have an edge against. Why stateless, you ask? That's a key feature of SLH-DSA. In some signature schemes, the signer needs to keep track of every signature they've made to avoid reusing specific values, which could weaken security. That's called a stateful system, and it's a hassle. Imagine having to log every email you sign. SLH-DSA ditches that requirement. It's stateless, meaning each signature stands on its own, with no record-keeping needed. This makes it practical for real-world use, whether you're signing one document or a million. Let's zoom out for a moment. NIST didn't pull SLH-DSA out of thin air. It's based on an algorithm called Sphinx Plus, which came from a team of cryptographers during Nist's post-quantum cryptography standardization project. Sphinx Plus itself builds on decades of research into hash-based signatures, going back to pioneers like Ralph Merkle, who invented the Merkle tree concept in the 1970s. Nist tweaked Sphinx Plus to create SLHDSA, optimizing it for security and efficiency. The result? A standard that's ready for prime time, approved for use in federal systems and beyond. So who needs this? Well, pretty much everyone. If you're a beginner, think of it like this. Anything you do online, shopping, banking, messaging, relies on cryptography to stay secure. Governments use it to protect classified data. Companies use it to safeguard trade secrets. Even your smart fridge might use it to talk to your phone. As quantum computers creep closer to reality, we need algorithms like SLHDSA to keep those connections safe. Nist Fips 205 isn't just for tech wizards, it's a foundation for a secure digital world that includes you and me. Let's talk practicality. Implementing SLHDSA isn't as daunting as it might sound. The document spells out everything developers need. The specific hash functions, like SHA-256 or SHAKE-256, the parameters for the Merkle tree, and the steps to generate and verify signatures. It even offers different security levels, 128-bit, 192-bit, and 256-bit, so users can pick what fits their needs. A 128-bit level might work for everyday apps, while 256-bit could protect top-secret files. This flexibility makes SLHDSA adaptable, whether you're coding a new app or upgrading a government server. What sets SLHDSA apart from other post-quantum options? For one, its hash-based nature gives it a unique advantage. Other Nist standards like Fips 203 and 204 use lattice-based math, which is also quantum-resistant but operates differently. SLHDSA's reliance on hashes means it's grounded in a well-understood cryptographic primitive. Hash functions have been battle-tested for years. Plus, it's already proven itself in the Sphinx Plus trials, surviving scrutiny from experts worldwide. That track record builds confidence that it'll hold up when quantum computers arrive. Now, let's address the elephant in the room. When will we need this? Quantum computers capable of breaking current encryption don't exist yet, at least not publicly. Experts guess we're 10, 20, maybe 30 years away. But here's the catch. Data you protect today could be harvested now and cracked later. A strategy called Harvest Now, Decrypt Later. That's why Nist is acting proactively. By standardizing SLHDSA and other post-quantum tools, they're giving us a head start to secure our systems before the quantum storm hits. If you're new to this, you might wonder how to get involved. Start by learning the basics of cryptography, terms like hash, signature, and quantum computing. From there, explore Nist's website. They've got resources galore. If you're a developer, dive into the Fips 205 PDF. It's dense but doable with some patience. For the rest of us, just knowing this work is happening keeps us informed citizens of the digital age. I hope you've enjoyed this journey through Nist Fips 205 and the world of post-quantum cryptography. It's a fascinating field that's all about protecting our future. I'd love to hear your thoughts. Drop a comment below with your questions or reactions. If you found this video helpful, give it a thumbs up, and don't forget to subscribe to Dr. Carminati's channel for more deep dives like this. Thanks for watching, and I'll see you in the next one.